Hello, welcome to our lesson on derivatives of log functions. So how are we going to take the derivative of something like f of x equals the log base a of x? This is really easy to do if we know the connection between logarithms and exponential functions, which we talked about in our previous topic. So a logarithm is really just that. It's an exponent. So a logarithm is simply a power or an exponent. For instance, if I had something in exponential form like a to the x power equal to y, this exponent can be represented using a logarithm. So we could say that the log base a of y is equal to x. So these are two equivalent forms here. Notice that the base of the exponential and the base of the log are the same, but again, the exponent that we have here, that exponent is the answer to this logarithm. It is represented by this logarithm. So when we say a to the x power equals y, it is the same to say that the log base a of y is equal to x. And one form is helpful for solving in different situations than the other, and the other might be more helpful in other situations. Okay, so the both forms are necessary, and so we should be able to work with either. But since they're connected, it's going to be helpful to use that connection. Now, if we're dealing with the natural logarithm, if I had e to the x power equal to y, our natural logarithm is always base e. So this would be the natural log, again with a base of e. Since it's always base e, we don't write it, of y equal to x. So the exponent here, again, represented by this natural logarithm. Okay? Now just again to recap this and make sure we're solid going from exponential form to log form or vice versa, I want to show you some concrete examples because sometimes when they're abstract with just the variables, it's like, wait, what? So for instance, if I said 3 squared was equal to 9, I could also say that the log base 3 of 9 is equal to 2. So the power here, again represented by this logarithm. So the log base 3 of 9 is 2 because 2 is the power of that base that makes this argument 9. Okay, or if I said 3 to the, let's say, 4th power was equal to 81. Again, I could say that the log base 3 of 81 is equal to 4. So my exponent of 4 represented by this logarithm. Or let's go one more power here. Let's say 3 to the 5th power, which is going to be 243, means that the log base 3 of 243 would be equal to 5. And with the natural logarithm, our base of e, let's say I had e to the 0 power. Well, anything raised to the 0 power is going to be 1, which means in log form we would say that the natural log, which is already base e of 1, would have to equal that power of 0. Or if I had e to the 1st, anything to the 1st power is itself. That means that the natural log, base e of e, would have to equal that power of 1. Or if I square e, I get approximately 7.4. So then the natural log of 7.4 would have to be approximately 2. All right, these are all saying that e to the 1st power, or sorry, e to the power of 0 makes 1, e to the power of 1 makes e to the power of 2 makes 7.4. So we read them a little differently when they're in log form, but essentially these are two ways to say the same thing, okay? So if we can differentiate an exponential function, we should be able to differentiate a log function in a similar fashion. If we can differentiate one, we should be able to differentiate, that means take the derivative of the other. So let's start with this f of x equals the log base a of x. Since right now I don't know, I mean I do, but I'm going to pretend I don't know how to take the derivative of this log function, I'm going to rewrite this in exponential form because I know how to take the derivative of an exponential. So if I was to rewrite this, I would say that my base a raised to my power, which would have to be f of x in this case, a to the f of x power is going to equal my argument of x. So this base to this power is going to equal this argument. Now that it's in, lost my place, now that it is in this exponential form, again, I can take the derivative. In our previous topic, we said if we were going to differentiate with respect to x, something like y equals a to the x power, that derivative y prime would be the natural log of a multiplied by the exponential function itself. Unless we changed our exponent x to something else, right? If we made it a little more generic, then we would also have to multiply by the derivative of that thing. Okay, so let's apply that here. I am taking the derivative of an exponential. So the derivative here would be the natural log of my base, so the natural log of a, multiplied by the exponential function itself, so a to the f of x power. And then because this is not just an x, I have to multiply by the derivative of it. Well, the derivative of f of x would just be f prime of x. And that's going to be equal to, on this side, when I take the derivative of x, I just get a 1. Now remember, what I'm trying to do is find the derivative of f of x. Well, I have that here, so now I'm just going to do a little bit of work to solve for f prime of x. So here, I'm going to make a replacement. I have this a to the f of x power. Well, I see that here is also equal to x, so I'm going to swap that out. I'm going to call this the natural log of a times x times f prime of x equal to 1. And again, if I want to solve for f prime of x, and it's being multiplied by x and the natural log of a, I'm just going to divide that over. So that means f prime of x, the derivative of f of x, is going to be 1 divided by the product of x and the natural log of a. And that is in fact the derivative for a log function. If f of x is the log base a of x, f prime of x is 1 over x times the natural log of a every single time. Okay? And we'll write that down again in a second, but I want to look at the natural log function as well. So I want to start this the same way. I'm going to rewrite this. If f of x is equal to the natural log of x, that means that e to the f of x power is going to equal that argument x. Now again, we talked about differentiating e to the x in our previous topic. We said if y was equal to e to the x power, then the derivative with respect to x of that would be y prime equals e to the x. So the derivative of e to the x is just e to the x. Unless we changed x, if x became anything else, like u, then we would have to also multiply by the derivative with respect to x of that u. So let's do it. Let's now take the derivative of this exponential form. So the derivative of e to the f of x is going to be itself e to the f of x. But this is not just an x here, right? So we have to multiply by the derivative of f of x, which would be f prime of x. And that's going to be equal to the derivative with respect to x of x is just going to be 1. Now, again, I'm going to make a little replacement here. This e to the f of x is equal to x, so I'm going to swap this e to the f of x out with an x. So x times f prime of x is equal to 1, and f prime of x is what I need. So if it's being multiplied by x, I divide that over and find that f prime of x is equal to 1 over x. So if your function is the natural log of x, its derivative is 1 over x, so just the reciprocal of x. So those are our derivative rules for log functions. The derivative of a log function is, we're going to call this the reciprocal of the product of the variable and the natural log of our base. So the product of the variable and the natural log of our base would look like this. Its reciprocal would be 1 over that thing. And so that's what how we're going to describe that here. So it's the reciprocal of the product of the variable, which in this case is x, and the natural log of the base, so natural log of a in our case here. And then remember, the chain rule can be used to generalize. If it's just a log base a of x, then we're just going to have an x here. If that x becomes anything else, we still have that same concept. It's 1 over the variable and natural log of the base, but then we have to multiply by the derivative of this thing. So applying the chain rule generalizes that derivative of a logarithm. And then if it's a natural logarithm, meaning it's our base of e, then our derivative is just the reciprocal of the variable. The reciprocal of the variable. So the derivative of the natural log of x is just 1 over x. And again, if x becomes anything else, then we also multiply by the derivative of that thing so that we can apply that chain rule and again generalize the derivative rule. Alright, so now that we have that down, let's try it out. Let's take some derivatives. If I was looking for the derivative of y equals a log base 4 of x. I'm going to say y prime is the reciprocal of the product of my variable and the natural log of my base. Done. So 1 over x times the natural log of 4 is my derivative. Or here, if I have f of x equal to the log of 10, just like with the natural logarithm, we don't write the base because we know it's an e. On this one, we have the common logarithm. When the base isn't written, there's an implied 10 there. So even though we don't see it, you have to recognize that this is the log with a base of 10. Okay, log base 10 of x. So when the base isn't written, that's our common log that has that implied base of 10. So let's apply again our derivative rule. F prime of x is the reciprocal of the product of our variable and the natural log of our base. And that's it. That's our derivative. Okay? Now, if we have our log function multiplied by a constant, or any function multiplied by a constant, we talked about a constant multiple rule. We said if we're taking the derivative with respect to x of some constant multiplied by a function, that the derivative would just be the constant multiplied by the derivative. So we're still just going to take the derivative of log base 5 of x, and then we're going to multiply it by 2. And if you wanted to, in fact, use your product rule here and call 2 your first function and call log base 5 your second function, the same exact thing is going to happen. So if you don't trust me or you don't remember the rule and you saw that as a product rule, it's going to work out the same way. It just takes a little longer to get there. So let's go here. Y prime is going to be 2 times the reciprocal of the variable and the natural log of the base. And this one, I would probably just take the extra step to simplify. When I multiply by 2 here, technically that's 2 over 1. That 2 belongs to the top of the fraction. So a better form of this answer would be 2 over x times the natural log of 5. And then you can get rid of some of those parentheses. Okay, so there's our derivative. Now, of course, we can include some other rules, product rule, quotient rule, more chain rule, but let's look at some pretty straightforward natural log functions, and then we'll start adding some of those other things in. So again, we have the natural log of x. This derivative is even simpler. The derivative for the natural log of x is just 1 over x. So if our f of x is natural log of x, again, f prime of x is just 1 over x. If it's a constant times the natural log of x, it's going to be the constant times our derivative. So here, y prime would be 7 times 1 over x. And again, I would clean that up and just call that 7 over x. And then if we have something other than x, remember we're going to apply that chain rule and multiply by the derivative of that inner function. So here, let's say f prime of x is equal to, it's going to be instead of 1 over x, 1 over x squared plus 1. And then we multiply by the derivative of that inner function, and the derivative of x squared plus 1 would just be 2x. And again, this is technically 2x over 1, so I'm going to go ahead and multiply that 2x to call my derivative 2x over x squared plus 1. I was about to box that in, then I had to go back and do all the other ones. Okay, now, g of x, back to a common logarithm, base of 2, so base of 2 of 3x squared. So again, we're going to apply our chain rule here because our inner function is no longer just an x. So g prime of x. We're going to, with a common logarithm, look at the reciprocal of our variable, which in this case is not just an x, is going to be 3x squared. That gets multiplied by the natural log of our base. And then because, again, this is not just an x, we're going to multiply by the derivative of that inner function. So the derivative of 3x squared would be a 6x. And again, I'm going to go ahead and just take that to the top of this fraction. So if I said g prime of x is equal to 6x over 3x squared times the natural log of 2. This would be an okay answer, but hopefully you're recognizing that we have a common factor here, so let's reduce. If I divide here by a 3 and an x, I would have just an x left. If I divide here by a 3 and an x, I would have a 2 left, so I can reduce. And I'm going to say then g prime of x is going to equal 2 over x times the natural log of 2. And there's my derivative. Now you might be tempted, I hope you're not, to reduce the 2's here. But this 2 that's on the top of the fraction is in fact a 2. This 2 is not a 2. This is connected to the natural log. This is the natural log of 2, and the natural log of 2 just represents some decimal, so you cannot reduce, and that's one of the reasons we like to keep these natural logs in parentheses so that we're not tempted to do those incorrect math things. Alright, let's look at the next one. So next one we have a logarithm, but it's being multiplied by a linear function. So this is a product rule problem. I have one function here times a second function here. So I'm going to call this one f and this one g. And remember, our product rule says f prime g plus fg prime. So in this case, we're going to say y prime, the derivative of the function, is going to be first the derivative of f, so f prime, and the derivative of 6x is just going to be 6. That's going to be multiplied by g. So I'm just going to bring g down as is, log base 3 of x. And then I'm going to add f, which is 6x, multiplied by g prime, so the derivative of the log base 3 of x. That is the reciprocal of the variable times the natural log of the base. Okay, so if you left it here, this would be fine. Again, I would probably just go ahead and multiply that 6x, so bring that to the top of the fraction, and call this 6 times the log base 3 of x plus 6x over x times the natural log of 3. Now you could, if you wanted to, get common denominators and add the fraction, but I don't really think it makes anything look any better. It definitely doesn't help us reduce anything, so I'm going to be perfectly fine with this as a stopping point. Okay, so there's the derivative there using the product rule. Now we're jumping over to a natural log. Now anytime I see a radical, I like to rewrite it with a rational exponent, so I'm going to take that step first here. So if g of x is the natural log of the square root of x minus 3, that's the natural log of x minus 3 to the 1/2 power. So g prime of x, our derivative, again, natural log of x would just be 1 over x. Well, this is a natural log of some new inner function, so it's going to be 1 over that new inner function. And then because it's not an x, we're going to multiply by the derivative of that new inner function. So the derivative of x minus 3 to the 1/2. That's using our general power rule, so we're going to use the chain rule again. So the derivative for x minus 3 to the 1/2 would be 1/2 times x minus 3 to the, let's subtract 1. 1/2 minus 2 over 2 would be negative 1 over 2. And then we have to multiply by the derivative of the inside there, which would just be a 1. Okay, so now we're here, and again, I would probably just try to clean this up a little bit. So let's get rid of the negative exponent first. Here we're looking at 1 over x minus 3 to the 1/2 being multiplied by 1 over 2 times x minus 3 to the 1/2. And then we're multiplying by 1, which is not going to change anything there. So then this becomes g prime of x of 1 over, on the bottom, we're going to have a coefficient of 2, and then we're going to add these exponents, right? If I multiply an x times an x, I get an x squared because I add those. That's what I'm doing here. So if I add a half and a half, I get a whole. Or think about if you were multiplying the square root of x minus 3 and the square root of x minus 3, I would get the square root of x minus 3 squared, which is just x minus 3. So the same thing is going to happen here. When I add the 1/2 and the 1/2, I get, no, I need to get rid of those circles. To back up a little bit, so sorry. There we go. When I add the 1/2 and the 1/2, I get a 1, so it's x minus 3 to the first, which I don't really need. So I'm going to go ahead and take this one more step and call this 1 over. If you left it here, that would be totally fine, but because it's an exponent of 1, easy enough to distribute, I'm just going to call that 2x minus 6. But again, either one of these would be totally fine as an answer. And actually, all of these are correct. It's just preferred to simplify in little ways if we can, because this looks a lot cleaner than this does up here. But as soon as your work to simplify does not make things look any cleaner, it'd really be okay to stop. Alright, so moving right along, let's look at number 10 here. Again, it's a natural log. If we're taking the derivative for a natural log, it would just be 1 over x, but this is not just an x. This is going to be a lot like the last one where we have to use the chain rule twice. So y prime is going to be the natural log, natural log of this thing will be 1 over, instead of x, it's going to be x cubed plus 2x cubed. And then we have to multiply by the derivative of that inner function, and that's going to require the chain rule. So the derivative of this piece would be 3 times x cubed plus 2x squared multiplied by the derivative of the inside, which would be 3x squared plus 2. Now this is technically all over 1, which means it's going to go to the top of my fraction. So we can say y prime is, and I'm going to go ahead and multiply the 3 by the 3x squared and the 2. So I'm going to have 9x squared plus 6, and I'm going to have this x cubed plus 2x squared, and that's being divided by x cubed plus 2x cubed, and that means we can reduce. I can get rid of both factors of the x cubed plus 2x here and be left with just one of them here. And so final answer we're going to say is 9x squared plus 6 over x cubed plus 2x. Now technically the numerator and denominator are factorable. There's a GCF at the top and the bottom, but that's not going to help us reduce anything. So again, I don't think factoring would be a necessary step, but this version looks a lot cleaner than this version, and the same looks better than this one. So I'm going to go with this as a good final answer and a good place to stop. Alright, let's look at one more. We're going to use a quotient rule on this one. This time it's a common logarithm, but hopefully clear that it's a quotient because we have a function up here, a log function up here, and then a different function is a linear on the bottom. So I'm going to call this f, I'm going to call this g. Remember, our quotient rule says we want f prime g minus f g prime on the top, and then g squared on the bottom. And so here, f prime of x is going to equal, we have f prime, so the derivative of the top. That's the derivative of a common log, so that's the reciprocal of my variable, which is 2x plus 1, times the natural log of my base. And then because this is not just an x, I have to multiply by the derivative of that thing, which is just going to be a 2. So that's just f prime right there. Okay? And in fact, if I multiply by 2, I already know that's going to go to the top of the fraction, so I'm going to go ahead and move that up here and call that a 2. Okay? So there's f prime. Now that has to be multiplied by g. So g is just an x. And again, wouldn't be that hard. So go ahead and just multiply the x and move it up here. Now from that I want to subtract fg prime. So I'm going to bring over f, which is just a log base 8 of 2x plus 1. And then that is going to be multiplied by g prime. Well, if I multiply this by g prime, the derivative of x is just going to be a 1. So I really don't need that there. And then we're going to divide by an x squared, g squared on the bottom. Okay, so now we're in this situation. I don't know how much work or what would be instinctive for you to do to clean this up. I'm going to go ahead and get rid of this multiply by 1 because I don't need that there. Again, multiplying by 1 is not going to do anything. And I don't want to necessarily do the work of subtracting here because getting the common denominator is going to make that look really bad. But remember what it means to divide by x squared. If I have something and I am dividing it by x squared over 1, I would say that's the same as multiplying by 1 over x squared. So dividing by a fraction is the same as multiplying by its reciprocal. So what I'm going to do is take this numerator here, and instead of dividing it by x squared, I'm going to multiply it by 1 over x squared, and that's going to get rid of this. Okay, if I multiply by 1 over x squared, then that denominator goes. Again, instead of dividing by x squared on the bottom, which is x squared over 1, multiplied by its reciprocal. So then I can easily distribute that. So when I multiply here and then multiply here, I'm going to end up with, let me see, f prime of x equal to 2x, and then here I'm going to have an x squared, a 2x plus 1, and a natural log of 8. And then I'm subtracting the log base 8 of 2x plus 1 over x squared. And this one, first fraction, can be simplified just a little because we have an x in common. So I'm going to get rid of one of those and get rid of that. And I'm just going to call this my final answer. Again, we could probably do the subtraction and try to get common denominators. I don't know that that's going to make anything look any better because you'd have to multiply all of this here, and that's, yeah, it's not, I don't think it's worth it, is what I'm saying. So 2 over, we got an x left, a 2x plus 1, and if you wanted to multiply that in there and call that 2x squared plus x, that would be fine. And then natural log of 8, and then log base 8 of 2x plus 1 over an x squared. Okay, so not terrible. And if you were taking something like, if there was a question like this on an exam, I'm going to have some flexibility in where you could stop with the answers. If you did a little bit of simplifying, that'd probably be good. I'm not likely going to put anything like this on the homework because it's really hard to get all that input there nicely, but this is something that you should be capable of doing. Okay, so hopefully it makes sense. All right, let's look at the last two problems, which are not overly difficult, but they do lead us to a secondary definition I just want to make sure that you've seen before. Let's say I was taking the derivative of the... Oh, I meant to change this problem. I'm going to change it now. Don't mind me for a second. I meant for this to not say this. I knew I was going to make an edit and then forgot. Let's call this the log base, not 8, base a of a negative x. Okay? And then I'm going to make this one can stay. So if I wanted to differentiate here, it's a little generic, but that's okay. I know how to take the derivative of a log function. I would say f prime of x is the reciprocal of my variable multiplied by the natural log of my base, and then when that's not just an x, I multiply by the derivative. Well, the derivative of negative x would be a negative 1. So if I multiply by a negative 1, the negative here and the negative here are going to cancel, and I'm going to be left with the exact same derivative I had when x was positive. So this would be 1 over x times the natural log of a. And the same thing happens over here with the natural log of negative x. If I said find the derivative of the natural log of negative x, again, natural log of x would be 1 over x. So natural log of negative x would be 1 over negative x multiplied by the derivative of negative x, which would be a negative 1. And the negatives would cancel, and so f prime of x would still be equal to 1 over x. Because taking the log or the natural log of the positive or the negative leads to the exact same thing, we can condense this into one definition using a symbol that I know you've seen before, and that's what I have over here. Because the derivative of the log of x and the log of negative x are the same, the two results can be combined into one rule using the absolute value. So I could say it's the log base a of the absolute value of x. So whether it's positive or negative, this is going to be my result. And the same thing here, natural log of the absolute value of x, its derivative, it's still going to be 1 over x. So whether this is positive or negative, it doesn't matter, but I end up with the same derivative. Okay? Now, I'm not really going to be referencing this one a ton, but if you're going on to the next level, or you're in a place where you see the log or your natural log with the absolute value there, it does not affect how we take our derivative. Just know that whether it's positive or negative, you get that same result. Okay? So I think you got enough to go off for your assignment, but if you have any questions, as always, just let me know. Until next time, take care.